The topic is area, and area is the number of squares that can fit into a shape, the number of unit squares. And a unit square has a side length of 1 and an area of 1. And the easiest thing in the world is to figure out the area of a rectangle, even if I don't draw it very well, because if you take the number of squares on the side and a number of squares on the other side and multiply them together, 1, 2, 3, 4, 1, 2, 3, you'll find out how many squares there are in the whole thing. Unfortunately, not all shapes are rectangles. Working slowly away from rectangles, we could look at parallelograms. Okay. And if you look carefully, you'll see that what happens when you make a parallelogram is that you're really taking this part of a rectangle and moving it over here, so that the rectangle and the parallelogram still have the same area, but it's not quite the same way to calculate it. Why not? Well, the base is still the base, but what was the height before was actually the length of the side. Now it's not. This is still the height, because if you were to come over here, just think of it as if it were a physically real place, and you have climbed to the very top, and you have taken a ball of string and tossed it over the side, and it lands on the ground. This distance from here to here is the height. It's the same as the height would have been if it had still been a rectangle, but it's not. It's a parallelogram now, so you have to actually figure out what the height is. There's some things that can help you with that, but that's what you have to find. Interestingly enough, if you're dealing with a rectangle and you turn it on its side like this, right, no big deal. Base, height. However, if I turn the parallelogram on its side, now it looks like this. Well, let's put him back up here. And say, well, throw the string off the side over here. That's going to be a different height. But it's okay because it's also a different base. And regardless of which base you choose, if you choose the appropriate height, it's still going to be base times height, because, take a look here, if I took this part of this parallelogram and moved it over here, I'd be back to having a rectangle. So the idea here is that although you may have learned base times height, it's not always quite that simple. Now, the other thing that happens is that sometimes you have a triangle. And you think, well, okay, base times height, but where do I go from here? Well, first of all, it doesn't matter what you use as the base. If we use this as the base, or we use this as the base, or we use this as the base, makes no difference. If you take the midpoint of a side and rotate the triangle 180 degrees, you have a parallelogram. Whether you do it this way, or whether you do it this way, or whether you do it the other way. No matter how you do it, if you take a triangle and rotate the side, any one of the sides, you'll wind up with a parallelogram, which means that a parallelogram is really two congruent triangles. Of course, that's not something new for us. We know that. We've known that all along. This is the reflexive property. This is congruent to itself. If this is a parallelogram, then this angle is congruent to this angle because they are alternate interior angles. And this angle is congruent to this angle because they're alternate interior angles. So, of course, angle, side, angle, these two are congruent. The area of the parallelogram is therefore twice the area of either one of these triangles. So how do we get the area of a triangle? Well, get the base and multiply it by the height, and then multiply it by 1/2. Again, if you have learned area is always base times height, this is where that will start to fail you, because it's not. So if I have a triangle that looks like this, I might take this height right here, or I might take this height right here, or I might even take this height right here, and if I've drawn them correctly, and if we measured this all out, if I take any one of the sides and multiply it by the appropriate base and then multiply that by 1/2, I will get the area of the triangle. Now, if you start to think of any shape that has straight sides, like this shape here, well, there's no formula for the area of this shape. There's no formula for the area of this shape, but you can certainly find the area of this shape if you break it into rectangles, parallelograms, and triangles. Now that shape's not all that easy to do. But it doesn't matter because area is additive. Now, you might say, well, wait a minute. This shape, it's really hard to split it up like that. Well, you're right. So if we did this, right, found the area of this rectangle and then just started subtracting the areas of the shapes that are not part of it, that would give us the answer too. Okay? Yeah?
How'd you find the base of that?
You don't need to find the base of that. It isn't base times height. You need to break this up into pieces and then look at the individual pieces. What's the base of this triangle? Well, this is, and this is the height. If I'm taking this triangle here and I'm looking for the area, well, I got to turn it this way and do this. If this is the rectangle that I'm taking the area of, then I got to do the base and the height. Okay? You're breaking it into pieces. Not every shape is just going to be base times height. to give you something a little more solid to deal with, right? What if I gave you that shape right there? Okay. And let's even, just to make it a little bit easier, let's just assume this is a straight line. How would you find the area of that? This is a rectangle. This is a right triangle. If you could get this distance here, this length here, this length here, and this length here, it would be pretty straightforward. Okay? Or you could say, well, wait a minute. I can get the area of that rectangle and subtract the area of this trapezoid. Oh, wait, how do you get the area of a trapezoid? We haven't done that yet. So here, trapezoid. Interesting thing about a trapezoid, it's actually two triangles. Break it in half with a diagonal. Both triangles have the same height. They just have different bases. So this triangle right here, if I use this base and this height, let's call this base 1. And if this triangle here, I use this height and this base, let's call that base 2, the area of the whole thing is 1/2 the base times the height for one triangle plus 1/2 times the base times the height of the other triangle. If you break this into two triangles, you've got yourself the area. Yes?
I thought the area of a trapezoid was a is equal to 1/2 times base 1 plus base 2.
Did you?
Yes.
Huh.
Like, I'm pretty, that's what it says in the book.
That's what it says in the book. Okay, so let's go back to what I said. Take a look. This is what I said, right? I said you break it into two triangles so you don't have to memorize anything other than just what you already know. If this is base 1 and this is base 2, I said we could get the area of this triangle by saying 1/2 the base times the height. The area of this triangle by saying 1/2 times the base times the height. Distributive property says I can actually factor out 1/2. B1H, B2. Wait a minute. Distributive property says I can actually factor out an H. And then if I multiply this, it's base 1 plus base 2 over 2 times the height. You know what? I don't really care how you write the formula. It's the same. Okay? And you can memorize anything you want, but the point I'm trying to make for you here is that you really don't need to memorize anything. This is something that you could figure out intuitively, which is great, because that's going to work for absolutely every kind of polygon. Right? I can take this, find a central point here, and break this into triangles. And if I have enough information about the triangles, all I got to do is add them together. This one's not so easy, because I'd have to have a lot of information. Have to have each of the bases, each of the heights. However, if you're dealing with a regular polygon, and by a regular polygon, we mean all of the sides and all of the angles are equal. And let's just assume for a moment that this, despite my drawing, is a regular octagon. We can actually find different pieces of this. First of all, we know that if we take the center and we draw radii, that's what these are. Each one's a radius. Together they're radii. And we draw them out this way. they're all going to be equal. Here, 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 here. These are all going to be equal. Here, 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 and here. And that means we actually have congruent isosceles triangles all the way around. So really then we only have to look at one of them. And then once we find it, we can multiply the area of that by however many there are, which is determined by how many sides there are on the shape. Now the question is, how are we going to find the base and the height? Well, if we look at one triangle, no matter how many sides the polygon has, from 3 sides to 150 to 600 sides to 1,000 sides, the process is always going to be the same. First of all, we know how to find the measure of an interior angle of a regular polygon. We did this last semester. It is the number of sides minus 2 times 180 divided by the number of sides. That's the measure of this angle here. The measure of this angle will be half of that, which means putting a 2 there, or, if you prefer, dividing this and making this 90. So this angle right here is going to be n minus 2 times 90 divided by n. And that's nice. We know it's an isosceles triangle, so we know that if we drop an altitude here, this will be a right triangle. This will be half of this. We know this angle here. This in a polygon is called the apothem. And it is the segment that you draw from the center to the center point of any one of the sides. Basically the height of the triangle. And using trigonometry, you really only need 2 pieces of information here to get everything else you need. This is a right triangle. If I give you this, you know this angle. If I give you this side right here, you can use that to get this side. If I give you this side right here, you can use that side and this angle to get this and this. If you know how to use trigonometry, you've got everything you need right here. This angle you can figure out. Depending on what clue I give you, the apothem, the radius, or the base, the side length, you can figure out these other 2 lengths. Once you do that, then you go back to thinking about this triangle right here. You know this height, you know this base. So 1/2 times the base times the height times however many sides there are is going to be the area of your regular polygon. There are a couple of situations where you can actually find exact answers as opposed to the estimates that trig usually gives you. If you have a square and you know the radius, well, that's okay, because actually you know that the diagonals bisect each other and form right angles. So this is actually a 45, 45, 90 triangle. That's nice. If you have an equilateral triangle and you draw radii like that. Well, now you know, right? Each one of these angles, here, here, and here, is 60 degrees. This is going to be 30. This is going to be 30. This is going to be 120. When you do the height here, now you've got a 30, 60, 90 triangle. Suddenly that's easy to do. Also, if you have a regular hexagon, same thing's going to happen here. 6 minus 2 times 180 is equal to 4 times 180, which is equal to 720. And if I divide that by 6 sides, each one of these angles is going to be 120 degrees. Here, 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 and here. Not only that, but when I start drawing my radii, I'm going to cut them in half. These will be 60 degrees. When I drop the altitude here, this is going to be a 30, 60, 90 triangle. You can use the special right triangles to get exact answers for these shapes. For the others, you have to use trig, which gives you estimates. But that's okay. It still works. One last thing. If we were to decide to make a regular polygon with as many different sides as we could make, right? And if it's regular, then all the sides are equal. The angle, the central angle, would be really, really small. Here's what we have learned by making smaller and smaller central angles and making polygons with regular polygons with more and more sides. If you do a chart, 3 sides, 4 sides, 10 sides, 90 sides, 180 sides, 360 sides, and you make the radius equal to 1, just to make your calculations easy. This radius right here is equal to 1. Well, little by little, the perimeter around it and the area, they converge towards a single number. And it turns out that the perimeter, as you go further and further, depending on how many decimal places you want to go, you can get closer and closer. Right? Somewhere around here, if you're just rounding it to 2 decimal places, becomes about 6.28. So it doesn't matter how many more sides you add, it's going to be 6.28. The area, $3.14. In other words, as you have more and more and more sides, this thing gets closer and closer to being a circle. And the radii become infinitely close to one another, so that basically anywhere you draw a line from the center to the circle, you're dealing with a radius. If this is 1, the calculations will show that the area of this will be something close to this. And if you go around like this, it'll be something close to twice that. Now, what that means is there is definitely a ratio of the distance all the way around a circle to the distance across a circle and through the center. there is the circumference, it's called a circumference when it's a circle, not a perimeter, and the diameter. There is a ratio there. If you take the circumference and divide it by the diameter, it will always be a little bit more than 3. And the fact is, that number is pi. Okay. And that means that the area of this is pi. The perimeter is 2 pi. If we started to dilate this and multiplied this radius by r, we know from our experience that the distance around would also be multiplied by r. So distance around here, and that's the circumference, multiply it by r. The distance across, multiply it by r. What do we know about the area? We know that the area of this would be multiplied by this ratio squared. So for our circle, we had a radius of 1. The circumference was 2 pi. The area was pi. If we increase the radius by a factor of r, this will be 2 pi r. This will be pi r squared. The area of a circle is equal to pi r squared, and the circumference of a circle is equal to 2 pi r. Now, no matter what shape I give you, let's say I gave you a basketball court. You can find the area of this. This is half a circle. This is half a circle. This is a rectangle. You can get the area of that. You can get the area of many, many shapes now just by breaking it up into smaller pieces. Now, there were some of you who had questions. What questions can I answer for you? Yes. Alex, do you have something?
I was going to ask you, like, how many sides could a regular polygon have that would be, like, make it like 1 degree for the 0 degrees that
Good question. You're asking me a question about infinity. Okay. Now, just taking a quick aside here. Do you guys know that? No? Never seen that? Right? Right? 0.9 repeating is actually equal to 1. Did you see that before? Yeah. For those of you who have, great. For those of you who haven't, it's sort of unnerving. Because, wait, if I just keep putting 9s here, when does it ever become 1? Well, yeah, I mean, it shouldn't be 1, but it is. How do you know? Well, I'll show you. Let's say 0.9 repeating is equal to x. Then let's say 0.9 repeating times 10 would be 9.9 repeating, and this would be 10x. Everybody okay with that? If I subtract them, this would be 9x. All these infinite 9s would sort of just subtract out, and this would be 9. And 1 would be equal to x, which was equal to 0.9 repeating. Wait, that's terrible. How about this? When we divide 3 into 1, we get 0.3 repeating, right? So that's why we say 1/3 is equal to 0.3 repeating. So multiply both sides by 3. What do you get? This is 3 over 3. This is 0.9 repeating. Yeah.
Isn't 3 over 3 1?
Uh-huh. Which is what I said to start with. Now, okay, one more little thing to hurt yourself with. Okay? This is called Zeno's paradox. This is from ancient Greece. If I want to go from point A to point B, I can't get there without getting past the halfway mark. When I'm at the halfway mark, I can't get there without getting to the next halfway mark. I can't get there until I pass the next halfway mark. I can't get there till I get the next. Wait a minute. I'm never, ever, ever going to get there. I can't. No matter where I am, there's still halfway to go. Of course, that's ridiculous, because if this were where I'm standing now, and this was a wall, and I took a running start, I'd hit the wall. Even though Zeno's paradox says that's impossible because you'd never really get by all the halfway marks. They're not imaginary at all, right? This is 1/2. This is 1/4. This is 1/8. This is 1/16. The next one would be at 1/32. Halfway from there would be 1/64. Whoops, 64th. Is there any end to that? No, there's no end to that. But this is the sign for adding things up, the summation. If I said, okay, I'm going to take all of these 1/2s, right? And that's what this is, 1/2, 1/2 squared, 1/2 cubed, 1/2 to the 4th power. If I take all of those and I go from n is equal to 1, and then just let n approach infinity, this equals 1. And if you're saying to yourself, how do I know that? Trust me, I have tried. Take a running start, and you will hit the wall. So now you're saying to yourself, well, wait, everything I have ever thought about life now is confusing, because you're telling me that when things get close enough, they're the same. And that actually is the foundation for calculus. So you're right there at the edge of this now. And the truth is, if you don't freak yourself out, it's not that hard, because you've already completely accepted the idea that I can walk from here to the wall. And you've already completely accepted the idea that if I make things infinitely small, they reach a certain point. Right? So the difference between 1 and 0.9 repeating is going to be 0. Wait a minute, wouldn't it be 0.0 repeating and then a 1? Yeah, except for one thing. If this is 0 repeating infinitely, when do you ever get to put the 1 there? Okay. So, going back for a minute. Your question was, how small can I make this angle before the polygon isn't a polygon anymore and it's actually a circle? The answer is, well, the answer is yes and no. The answer is, when this becomes infinitely small, this is a circle. But if you give me any particular size, I can always divide it by 2 and tell you there's a smaller one. Exactly. Now, the equation for the area of a circle and the circumference of a circle comes from that concept that we just talked about. That is something just to play within your mind, but it is actually where you are headed if you stick with it. All right?